Success. Okay. So it's the second revision seminar for summer semester 2015. And I'm going to have to talk about some infinite series stuff. Okay, so I want to talk about intervals of convergence because the examples that I have of that in the other revision seminars didn't record, so I want to talk about that. And I had some people ask me about the binomial series and also about some of the proofs that are there. And so I'll just talk about all of those things, and then you can ask me any and make your Taylor series. So we'll see how we go. Okay? But I do want to talk about a few things first, and I'm going to start with interval of convergence. Huge. You can zoom out. Okay. Right. So just to orient you and the listener to where we're up to, this is quite near the end of the section on infinite series and Taylor series. And I just need to remind you of a couple of things. This is called a power series. I leave off the sums here because it doesn't actually have to start anywhere, it just has to go to infinity. I'm just going to put a question mark there because it doesn't have to start at 0, it could start at 1 or 2 or anything, as long as it starts somewhere and goes to infinity. And I don't use an AN here for reasons that I hope will become clear shortly. This is called a power series. And a power series is just like a formal written statement. It doesn't necessarily have an actual number that it works out to for any particular x. The point is that if you sub in an x, you will get a series. Okay? So it's almost like a function. And it takes x's and produces an infinite series. Now I'm just going to rub something out here, which is the point I really want to make. It doesn't have to be bn x to the n. It could be x minus something to the n, or plus something, if you like. So it takes x's and it produces infinite series. So you pick a particular x, you get an infinite series. You pick another x, you get a different infinite series. You pick another x, you get another infinite series. And each of those series, sometimes they converge and they represent a proper number if you add up all the sums to infinity, and sometimes they don't. Okay, and you're really interested in whether they do or they do not. Okay, so about this infinite series, I could ask myself, in the Spanish sort of way, does it converge? Meaning, is there a number... That's really badly written, sorry. Does it converge? Is there a number that that infinite series represents? Okay? So, the interval of convergence is the x's that you can put in here and come up with the answer yes, that it converges. Okay? If I think about all the x's that I'm allowed to put in this spot and produce an infinite series, and then ask the question, does it converge? The interval of convergence is a way of going direct from here to here. The interval of convergence. It says, given the x, can I go directly to the answer of does it converge? So it's all the ones for which you would say yes. Okay, so interval of convergence is the set of x's for which the resulting series converges. Okay, that's what it is. Right, and all the other x's doesn't converge. So we usually don't even consider those x's. If we stick an x in there, it just gives us some fancy little maths thing that we could write that has a sigma in it, but that thing doesn't mean anything. It's not a proper number, it's just this thing we could write down. Okay. So, the theorem, I don't know which number it is, I don't even think it even has a name, but the theorem says that the interval of convergence is actually a proper interval. Okay? Otherwise it would just be the set of convergence. Okay? It's not just a set, it happens to be a proper interval. It means it has a lower end and an upper end. Okay? It may go forever in both directions, but it has a lower end and an upper end. And the radius of that is half of the distance between it. So the idea is that it actually is a convergence. Is an interval. It has that number c that I mentioned earlier up here. That number c is in the centre, and it will go some distance up and some distance down. And there will be an interval like that, which may be closed on one end or open on the other end, or closed on both ends or open on both ends. That will describe all of the x's at which you can get a convergent series. Okay, so the point is that it's not just an interval, it's an interval centred on that number c that was up there in my series. And when we talk about centres and widths, well, that's what a radius means. Radius means the distance from the centre to the edge. So this number here is the radius of convergence. Okay. So from knowing what the centre is, you always know the centre is that number c, and figuring out the radius, you can figure out almost everything you need to know about the interval of convergence except what happens at these, sorry for the video, at this end and this end, and you have to do that separately. Okay, that's the philosophy of the whole thing. And Ray said in the lecture, that means that if you happen to know by some magical reasoning that it converges here, then it must converge everywhere between there and C, because of the way that this thing is constructed. Okay, so let me do an example of finding one. I may change that 0 to a 1 shortly. Just give me a second. Yep, it will be a 0. So that's 2n plus 3 all over 6 minus n. And x minus 1 to the power of n. So that number c I was pointing out, the centre, is 1 in this case. Alright, so the way that you find the interval of convergence is use the ratio test. And if I were doing this in an exam, I would write the words ratio test, so that they knew, even if you couldn't finish it, that you knew that that's what you were supposed to do. Okay? And that they can tell what you're doing. So we're going to do the ratio test. And in the ratio test, we talk about the absolute value of an plus 1 over an. Okay. Right. Now when they say that an, they mean all of this. And that is why, when I write down the formula for a power series, I use a b here, just to remind me that all of that is the an. Okay? Not just this number here, but the whole thing is the an. Okay. So, that means I'm going to get, on the bottom, exactly what I have here. And on the top I'll have exactly this, but with all the n's replaced with n plus 1s. Like that. Now, I write it this way, and then sort of skip most of it. Okay, so let's just walk through this. X minus 1 to the n plus 1 divided by x minus 1 to the n. Well, that's almost all of these, and so that will cancel with this and leave me with an x minus 1. Okay, because if it was x minus 1 to the 4 over x minus 1 to the 3, that would leave me with just an x minus 1. Okay, that's a good start. And then this bit, well, when I divide by a fraction, I flip the fraction upside down. Okay, excellent. So what do I get? 2n plus 2 plus 3. Right. It's not looking good. That's okay. We'll be fine. So the next stage is that we actually need the absolute value of all of that. So I could have, if I wanted to, just chuck big absolute value signs all right in the top, all along the way, but I have the tendency to get confused when I do that. So remember, when you do absolute value, you can do the absolute value of each piece separately as long as they're multiplied together. If they're added, no hope, but if everything's multiplied, you can do the absolute values separately. And that's really important. This thing being in an absolute value sign all by itself is an important part of the working here. So the next stage is that what we're supposed to do is we're supposed to do the limit of this as n goes to infinity. So you can either just do like an arrow, or you can actually write the word limit in. It doesn't matter either way. And so the best way to figure out what the limit of something as n goes to infinity is to divide top and bottom by the biggest power of n that you see. And I could have expanded this out if I wanted, but I can't be bothered. But if I do expand it out, I'm going to get an n squared. And if I expand this out, I'm going to get an n squared as well. So that's the thinking that I need to think. So I need to divide the top and bottom by n squared. And what that's equivalent to is dividing this by n and this by n and this by n and this by n, and that'll do it. Okay? So the other way of thinking about it is to look at each piece, and they should all have the same powers of n in them, and divide each of them. So this bit and that bit by n, and this bit and that bit by n, and so we're going to get. So I divided each of those pieces by n on the top and the bottom, and that was okay because I did it on the top of the fraction and the bottom of the fraction, so it all comes out all right. And then I do as n goes to infinity, as n goes to infinity, this approaches 2 minus 1 minus 1, 2. Oh, that's totally not what I was hoping for, but that's okay. Okay. Which is just x minus 1. Yay! Okay. So that's the deal. Let's just look at what we did there. We did the an plus 1 over an we figured out the absolute value, we did the limit, and we got this final answer. They're the 3 steps that you need to do. Well, possibly just 2, but we need to do this part, and then we do the limit, and then we get a final answer. The key to all of this is the ratio test says that if the final answer that we get there comes out to less than 1, then it'll converge. And if it comes out to greater than 1, then it won't. So the next stage, in order to make my workings make sense to the reader, is I say to converge, we must have this final answer that we just got being less than 1. I'm going to do another example in a second. Once you get it to this stage with an absolute value like that, absolute value of x minus something, less than answer, this answer that is just here, that's the radius. The radius of convergence is 1. If all I wanted to know was the radius, you would stop there. But it also doesn't just tell us that, the centre is also 1. Okay, centre 1, radius 1. So in terms of the picture in our head, which I will draw short, picture in our head, we have the centre is 1 and the radius is 1. So it goes from 0 to 2. So my interval of convergence so far looks like this. It goes from 0 to 2. My question is, should I be colouring in those endpoints or not? Am I supposed to colour in the one at 2 because it converges there? Am I supposed to colour in the one at 0 because it converges there? Don't know. I have to figure that out. Okay? If you want another way of getting to this stage, then you can do it from the statement that I had here. When a mod is less than something, that means the same as that whatever that thing is between the plus and the minus. So if you see mod is less than whatever, that means that that's between here and here. And then if I add 1 to all 3 of them, I will get this, which is precisely what I drew in my picture. Okay, so my question is, should I be colouring these in, which means should I be putting an or equal to on this statement about x? And so I need to just investigate what happens at those endpoints. So when x equals 0, I go back to the very original formula. That's what I get. And I need to somehow tell if that converges without using the ratio test, because I've already used the ratio test. And the ratio test for this series will come out to precisely the answer 1, which tells us nothing. So I have to tell if this converges without using the ratio test at all. Oh dear, how am I going to do that? Well, the first rule of testing if series converge is to see if the individual terms go to 0. And if the individual terms don't go to 0, then it doesn't converge. So the limit so just do the absolute value of an all by itself. When you do an absolute value of a minus 1 to the n, it goes away. We'll divide everything by n again. And we get the absolute value of minus 2, which is 2. Right? Which goes to, oh sorry, just a second. There should be an arrow here. That approaches minus 2 as n goes to infinity. Sorry about that. It's not an equals. And so that's equal to 2, which is not 0, so it doesn't converge. So if you just get a plain old series and you do the limit of the individual terms and it doesn't come out to 0, it doesn't converge. You come out to any number, it come out to 0.003 and it would still not converge. When x equals 2, we get this. Because 2 minus 1 is 1, and 1 to the power of n is 1. So we get this. And again, that's going to have the same trick happen to it. So the absolute value of an will come out to, will approach 2 just like it did before, which is not 0, so it does not converge. And so therefore the interval of convergence is from 0 to 2, not including either endpoint. I'm going to do another example that comes out to a different answer. Just give me a minute to try and construct it because I wanted to show some important things.
Okay, can I just ask,
Yep.
if you break those values 0 and 2 and you put that into the s minus 1 term, does it give you any clue that that's, you know, like the harmonic series stuff?
That's exactly the example I'm about to do.
So you don't, but like you still have to consider all the n business on the left. 'Cause you don't know immediately, do you?
You might.
Okay. Right.
Yes.
You put x equals 2 and it came out to 2. Does that mean it converges?
What came out to 2?
X equals 2 and
No. The individual terms, like this thing, is 2 out of infinity. So when I go far enough, it's just plus 2, plus 2, plus 2, plus 2, plus 2, plus 2. So I just keep adding more 2s, so the answer is infinity, so it doesn't converge. Yep.
So you're saying it converges within the interval but not at the ends?
Yep.
So that's what's happening.
That can go all the way up to, you know, you could have x equals 0.00001 and it'd be fine, but if I put x equals 0, it doesn't work. Okay, just another example. I will attempt to construct one that will work. Alright. No. If I put a factorial in, it's going to converge for every possible x. So I need to put 2 in them to cancel each other out, but I don't like doing that. So I will. Yeah, I'll leave it as it was. And we'll see how we go. Yeah. Okay. Just an instinct for you. If you end up with a single factorial on the bottom, it doesn't make the slightest difference what's on the top. If there's a factorial on the bottom, it will converge for every possible x. That's just what's going to happen. So you should do the working properly, but at least you've got some instinct of where it's going to go. Because that just makes it look like the Maclaurin series for e to the x. So, okay. And I can start at 0. Okay. So I'm going to ask myself, does this converge? Well, I chose this for a reason. There are 2 things that we want to do. Before I go any further, I should probably simplify it. And I need to show you something. Right, n factorial is 1 times 2 times 3 times 4 times 5 times blah 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 times n. And n plus 2 factorial is 1 times 2 times 3 times blah blah blah, blah times n plus 1 times n plus 2. So there's this cool trick you can do which makes them come down to lower numbers. N plus 2 factorial is n plus 2 times n plus 1 times all the same stuff from n factorial. So to get the answer n plus 2 factorial, I have to do all of n factorial and then times by n plus 1 and then times by n plus 2. And then these cancel each other out. Yay! So therefore my AN is actually okay. So I need to do the limit, do my ratio test. So I should point out that that step there normally doesn't happen until you do the ratio test. Okay? But if you can simplify before you start, it's usually a good idea. But usually that step of cancelling out factorial stuff doesn't happen until later. So your ratio test, I need my AN plus 1 over AN. So n plus 1 plus 2 is n plus 3. N plus 1 plus 1 is n plus 2. I did skip a step there where I subbed in n plus 1 into this and got n plus 1 plus 2, which is n plus 3. Okay, so this divided by that leaves me with a 2x minus 3. And then that ends up on the bottom. Sorry, that thing that was on the bottom of the bottom ends up on the top. So I end up with this. And neatly they cancel, which is nice. So when I do my absolute value, you get that. And then I need to do the limit as n goes to infinity. So I did do the other version of it where I actually just write the limit in. You can do it with an arrow, but you can also do it this way. Okay, so that 2x minus 3 doesn't involve an n, so it's not going to come up when I do my limit. And the limit of n plus 1 over n plus 3 comes out to 1, because if you divide everything by n on the top and the bottom, you'll get 1 plus 1 over n and 1 plus 3 over n. So we're going to get 1 times. So that's my ratio test almost done. The final step in the ratio test is to make the statement that that needs to be less than 1 in order to converge. But before I do that, I really would prefer it was written as mod x without that 2 there. So I'm just going to factorise the 2 out. Okay, so I've divided both of those by 2 so that I can bring the 2 out the front. And I get this. This whole thing needs to have a mod x minus 3 on 2. Like a mod x minus something, so it's easier to see what's going on. So to converge, we must have, well, not must have, but whatever. To converge, we must have that answer that we just got to be less than 1, which means mod has to be less than a half. So you could have done this working here later, and that would have been fine. But now we can see that's the radius, and that's the centre. So my radius is a half. So if all I wanted to do was find the radius, I would stop there. So the next line of the working, I could take whatever I had here, which was x minus 3 over 2, and put it between plus a half and minus a half. And then I could add 3 on 2 to all 3 of them. So 3 on 2 is 1 and a half minus a half is 1. oops, I got rid of the 3 on 2, sorry about that. So now I have that my x is between 1 and 2. Let me just draw the picture to just make sure I've got that right. My centre was 3 on 2, which is 1 1/2. I go up a half, and that gave me 2. I go down a half, and that gave me 1. So my question with my interval of convergence is, do I have to colour in those 2 endpoints, or just maybe one of them? So I'm going to have to sub my x back into my original function. Let's see, at x equals 1, we get two times 1 minus 3 to the n over n plus 2 n plus 1. Like that. So we end up with minus 1. That's what we get when x is 1. And we look at that and we say, can I tell if it converges? Well, this one we can. So that minus 1 to the n, that makes it an alternating series. An alternating series is, in order to converge, all you need is for the bottom, for the total answer to be strictly decreasing, which it is. Because as n gets bigger, that denominator gets bigger, which makes the fraction bigger. So we have alternating series with an approaching 0, so therefore it converges. Cool. So actually what we need to do is colour in the 1, because it converges there. What about x equals 2? So 4 minus 3 is 1, 1 to the n is 1. You will notice that this will happen every time. One of them will be alternating and the other one won't. So basically that's what's going to happen. At one end you'll get a 1 to the n, and the other end you'll get a minus 1 to the n. And so now we need to tell if this converges. Now it's not alternating, so that's not helpful. The bottom is roughly n squared. It's n squared plus 2n plus 1. So, you have been shown a series that does have an n squared on the bottom. If you had this series, if it was just 1 over n squared, that will converge. 1 over n to a power will converge if the power is more than 1. That's one of the things you're supposed to remember. So 1 over n squared will converge, and each of these terms is less than that because each of those numbers is bigger. So by comparison to 1 over n squared, it does converge because it's roughly equal to 1 over n squared. So approximately
it's okay for us to say that.
Yep. It's not even approximately equal to, it's, each term is less than. Each term is less than that one, and so it converges because that one does. Okay, so that means I have to colour in the 2. So the interval of convergence is actually from 1 to 2. The other thing that can happen is it will converge at one end and not the other, and that will usually happen when, if this came out as a 1 over n, then this end wouldn't converge because it's a harmonic series, but the other end would because it's the alternating harmonic series. So, yeah. So I should just write that down. If you had x equals one end, whichever end that is, and it came out to minus 1 to the n over n, you would know that this converges since it's the alternating harmonic. And it doesn't matter if it's n as long as it's linear in n. It could be n plus 1. Okay, and that would be okay. And if x was the other end, and you get just that, then this diverges. Because it's the harmonic. And so you'll get the interval of convergence will look like something like that. That's a classic exam thing to happen. That it'll converge at one end but not the other. To show that you know about the harmonic series, basically.
What I was asking before, David, sorry, is like in that case you've got the alternating harmonic on the top and n on the bottom, so you know. But in one of the examples earlier, you ended up with minus 1 to the n, but multiplied by another fraction involving n, which didn't converge.
Yeah.
So how careful do we need to be, like making that assumption too quickly, like saying, oh, I can see the minus 1 to the n, so it does or doesn't converge?
So for the recording, the question is, like, in this one we got 1 over n, the other one there was like some fraction next to it involving n. Unless it's just 1 over something, you have to do the proper limit of what's next to it.
Right.
Okay, so before I did the limit of what's next to it, just to see what it came out to. So, but unless it's just 1 over something, you have to be careful. If it's just 1 over something, you can just say, well, it's an n cubed. It's approximately n cubed, it'll converge. Or it's approximately n, and so it won't if it's not alternating. So, yeah, but they will usually in an exam make it fairly obvious. Cool. All right, how long have we been going for there? Okay. Now, someone did ask about the binomial series, so I'll have a chat about that. And my heading will not be the binomial series. My heading will be Taylor series you're allowed to just write down, unless specifically asked to calculate them. I will not write all of that, but that's the real heading. Okay? So it's like known. And in fact, they're Maclaurin series. Okay, so there are some series with x's in them, like power series, that you are expected to just know. Alright? You don't have to do all the fancy f dashed a divided by n factorial crap, because you're supposed to just know them. If they specifically say, find the Maclaurin series for sine x, then you have to do all the derivative stuff. But if they don't say it, you're allowed to just write it down. Okay? And there are classics. There are 4 main classics, and then there's one more, which is the binomial series. So here we go. We've got geometric series, the geometric series 1 over 1 minus x. If you find the Maclaurin series for that, so you've got f dash 0, f double dash 0, and all the n factorials, you will get this. Okay? When it was first introduced to you, it was the other way around. You saw the series to begin with and you managed to figure out what it was equal to. But this is the Maclaurin series for x to the n, and only works if the absolute value of x is less than 1. So if x was a half, the answer would be 1 over 1 minus a half, which would be 2. And that's the geometric series. You're supposed to just know that. Your exponential series, So e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. No matter what x is, converges for all possible x. So the radius of convergence is infinity. And that's the reason why my t-shirt works. So that exponential series is the one, you're just supposed to know that. I'm not sure if they expect you to remember the sine and cos, but it can never hurt. So there's two ways of writing it, depending on what you're aiming to achieve, because sometimes they expect you to use like just the first 4 terms in the sine series. Okay, so sine x is an odd function, and so it only includes odd powers of x. Okay? If you've got an odd function, you'll only get odd powers in your Taylor series. If you've got an even function, it'll only have even powers. So sine x being an odd function only has odd powers, and they flip between plus and minus. That's how I remember it. So it'll start with the first odd power, which is x, and then it'll be minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus, and so on forever. It's exactly the same, well, not exactly, but yes, exactly. These terms here are exactly the same as the terms from e to the x. It's just that I've only got the odd ones and they switch between plus and minus. So the way of writing that is to say, well, it's only the odd ones, 2n plus 1. That's how you get an odd number, 2n plus 1. And it switches between plus and minus. But it's not minus 1 to the 2n plus 1, it's just minus 1 to the n, because only every second one of them switches. So that's how I remember the sine series. I write this down, and then I write this down. And I'll just say sine n cos. Cos x, it's the same trick. It's e to the x, but it's only got the even powers, and they switch between plus and minus. So it's 1 minus x squared on 2 factorial plus x to the 4 on 4 factorial minus x to the 6 on 6 factorial, and so on. And so you'll get, same as e to the x, but it's 2n now because it's only the even powers, and it switches between plus and minus. Cool. That's how I remember them. For your information, not that you need to remember it, cosh and shine are the same, except you don't have the minus 1 to the n. So without the minus 1 to the n, it will be shine x. And without the minus 1 to the n here, it will be cosh x. Which is super cool! And then there is the binomial series. Right. I find the binomial series, it took me years to figure it out. I had not the slightest clue what was going on when I was in first year. It's like, yeah, no idea. None. In fact, when I first had to teach 1B, I couldn't even remember that it was even mentioned when I did it. So it was that bad, it just blocked the whole thing out. So I figured it out now. The binomial series is the Taylor series for 1 plus x to the k, no matter what k is. Okay, and it only converges, if k isn't a nice whole number, it only converges when x is less than 1. Okay, so I'll write that down in a second. Just like all the others, and it's still got like an x to the n here. The k comes into it in the coefficient of x. And what you do is you do k choose n. So it's beautiful. It's all very simple. But in order to make this work, we have to redefine what we mean by k choose n. Okay? And we make that definition purely so that this works. Like that's the whole point of us making this new definition of what k choose n is. We only do that so that this Taylor series works. Okay? The whole point of this is for us to be able to just write down the coefficients without having to do all our derivatives. Okay? So just want to point out that it converges for mod x, for all x, if a number k is a positive whole number, and for mod x minus 1 otherwise. Because k being a positive whole number we care less about, but it's important to point that out. Okay. Actually, it doesn't. K could be 0 and it'll work too. So for all x. Okay. So here we go. The other thing that makes this work is our definition of k choose n, and this is our definition of k choose n. So there's two parts to this definition. The definition is 1 if n equals 0. It's always 1 if n is 0. I'm going to include this as a separate part of the definition, but you don't technically need it, but it just helps us understand what's going on. It's always k if n equals 1. And then you do this trick. You write a fraction. On the bottom of the fraction, you put n factorial. But in my head, it's way easier just to write the whole thing. Okay, so that's n factorial. And then on the top, you put the same number of pieces. So this has got n numbers multiplied together. On the top, we're going to have the same number of pieces, but instead of going up each time, we're going to go down. So we're going to start at k, we're going to multiply by k minus 1, and we're going to keep going until there's the same number of them. Now, that's all lovely when you write down and there's a formula and you go, what the rebel does that mean? And so we're going to just do a couple of examples of figuring out what k choose n is for k's other than, well, let's see. Okay, 16 choose 4. Well, let's see. So this is an ordinary choose. We used to know how to do this already. So on the bottom will be 1 times 2 times 3 times 4 because that's what you always put on the bottom. And on the top, you start at 16 and you work your way down. 16 times 15 times 14 times 13. And then you'll stop. And that is 16 choose 4. Which will come out to something horrible. A very large number. At this point, I start cancelling down, you know. So 14 times 13 times 10. 13 squared would be 169. Plus another 13, 182. I think. Someone may want to check that for me. Actually, I've got a calculator. I was right! Look at that. Great. Okay, cool. Next. Five choose 6. Alright, so So on the bottom we'll have 1 times 2 times 3 times 4 times 5 times 6. You can put the 6 factorial if you like, but it just helps me focus when I do this. So on the top we'll have 5 times 4 times 3 times 2 times 1 times 0. Yay, the answer is 0. In fact, if they're both whole numbers and the bottom's bigger than the top, it'll always be 0. So n choose n plus, something. So n choose n plus something, it's always 0, as long as they're whole numbers. Alright, well let's do one that's a bit better. -3 choose 4. Well, 1 times 2 times 3 times 4 over -3 minus 4 minus 5 minus 6. So, hoping you get the idea. The bottom is the factorial, and the top you have the same number of pieces, but you start here and work your way down. So all those minuses will cancel out because there's an odd number, even number of them. 3 will cancel, 2 and 3 will cancel with the 6, so that'll be 15. Yeah, okay. If you want a nice show of David being, super excited by combinatorics, get me to tell you all about negative binomials one day. Yes, super fun. I'll tell you now. So look at this. 16 choose 4 is a number of ways to choose 4 things out of 16 things, which is why 5 choose 6 ought to be 0. You can't choose 6 things out of 5, so there's no answer. But -3 choose 4 is a number of ways to choose 4 things out of 3 things if you're allowed to put them back every time. So cool. Anyway, one more. A half choose 3. So on the bottom, 1 times 2 times 3. On the top, a half. I'll go down 1 and I'll end up at -1/2. I'll go down another 1 and I'll end up at -3 on 2. So what have we got on the top? Like 3/8 divided by 3 will be 1/8, divided by 2 will be, and so it'll come out to a 16. Okay, that is the binomials. And now we can use the binomial theorem. Anything that looks like 1 plus x to the something, we can write down the first several terms of the Taylor series. We don't have to actually write down the infinite sum, because you know what? The infinite sum just looks like that. But we can just write down the first few terms. So 1 plus x to the half, that's root 1 plus x. So it'll be a half choose 0 plus a half choose 1 times x plus a half choose 2 times x squared plus a half choose 3 times x cubed plus and so on. That's how it always works. And so a half choose 0 is always 1. A half choose 1 is a half. A half choose 2, 1 times 2 on the bottom, a half times minus a half on the top. And a half choose 3, we just figured that out, but just for completeness' sake. So the first few terms are 1 plus a half of x, plus, minus an 1/8 of x squared, plus a 16th of x cubed. So that means that if x is quite close to 0, I can figure out the square root quite accurately, even with just the first 3. So if x was 0.1, for example, then root 1.1, which is 1 plus 0.1 to the half, would be approximately equal to 1 plus a half times 0.1 minus an 1/8 times 0.1 squared. And that approximation would not be too bad. That's what this is. And the actual root for 0 is 1.0488. So the real answer awesome, right? That is so cool. Right. So that's using it, and you can then do, almost, anything that you want now. If you see a 1 plus x to the power of whatever, if you can rewrite what you've got as 1 plus x to the power of whatever, you'll be able to do it. Like that. Like that. So that's not quite right? Because it should be 1 plus x. So let's just figure out what it would be if it was 1 plus x. So 1 plus x to the minus 1 will be minus 1 choose 0 plus minus 1 choose 1x plus minus 1 choose 2x squared and so on. Which would be 1 plus. So we've got 1 times 2 minus 1 times minus 2. I'll just do the next one just to be sure we've got the pattern right. 1 times 2 times 3 minus 1 times minus 2 times minus 3. Oh, that's interesting. That's always going to happen, isn't it? Look, the top is the same as the bottom, but they're all minuses. So we're going to get 1 minus x. The top will cancel with the bottom, and the 2 minuses will become a plus. This one, the top will cancel with the bottom, but there's 3 minus, so it'll be a minus. Awesome! There we are, yay! And so now if we want the 1 plus x squared to the minus 1, well that's okay, we'll just sub in x squared. Here's the really cool bit. Right. So, if I integrate 1 over 1 plus x squared, I'll get arctan. Right. So cool. So I just integrate it. Taylor series for arctan. So excited. Yay. But the point is, the whole point of the binomial series is this thing here. You can always write this line down because it's always the same. It's choose 0, choose 1, choose 2, choose 3. You just keep the number at the top all the same. And then you can always write down this next line because we know how to figure out what minus 1 choose 3 is, or what minus a half choose 3 is, or whatever else we wanted. Right. Well, it's 11 o'clock. I will now ask if anyone has sort of one more question, because I wouldn't mind eating before drop-in centre opens. So about half an hour if you want to stick around. Otherwise, you can leave. But have you got any questions about that or anything else in, say, this section of the course? So the moral of this tale is you're allowed to just write that down, okay? Unless they specifically say, show working to find the Taylor series for whatever, you are allowed to just write down that this is what it is. Cool. Now, so we check. Right, that'll probably do for now. Look, drop-in centre's open the next 3 afternoons. Feel free to drop in and ask any questions, and best of luck with your study. You don't need luck with your exam.